so many guys doing calculus out there.
It's true. So there are resources out there.
Yeah.
Okay.
Well, there's the best resource is your own professor because you kind of know.
Absolutely. Your best
Yeah,
resource.
Burns is the best.
That was unsolicited, okay? Just so people know. Okay, we're going to finish up the chapter. We finish up today. But first, I will take any questions you have on anything. Melissa, what do you?
I'm gonna have questions on Thursday.
That's fine. Thursday is for review, for questions, and the lab. We'll do that on Thursday. Monday will be your last hour exam. We got Thanksgiving break. We'll come back from Thanksgiving on that Monday after Thanksgiving. Is that when I'm giving you the first of the two finals, or
Yeah.
Thursday? Is that what I said?
You wrote it's on.
I wrote it. I wrote it
I'll
somewhere.
look it
It's all,
up.
no, I've got it.
No final, we're done. Task 4, 11, 24.
Oh, no, the very first day, December 1st, is review topics for the final, and I will go over the test number 4. December 4th is your sample final, and December 8th is your final, okay? So keep that in mind. That's what the schedule looks like, okay? And today we're doing the max spin and differentials, like I said.
Didn't we do that at the beginning though?
What's that?
Or was that just introduction?
That was introduction.
Introduction.
Yeah, we did talk about it a little bit. We talked about relative max and relative min, but these are the applied problems we're going to do tonight.
Now, is this for graphing also? Is that the purpose?
No, not really, although sometimes it is useful to graph a problem. Sometimes it's very useful. All right, any questions on homework then? Carolina, you okay? You all set? All right. All right, let us begin. Probably the best way to begin this is to do a max min problem. Let's do one. Okay. Here's the situation. Let us suppose we have a river, and we are a farmer, and what we want to do is build a rectangular enclosure that borders the river. Okay. Like so. Now, let's suppose that we have a certain set amount of wood to use for our enclosure. Let's suppose the amount of wood that we have is equal to 3,000 feet of wood. That's a lot of wood. Okay, but that's the way it goes.
What are we doing? Building a dam?
We're building an enclosure, rectangular enclosure that's going to border the river.
Like a pool?
Like what?
An enclosure
For the cows.
Well,
like a fence?
Like a fence. Thank you, a fence. We want to keep the cows in, but we want it to border the river.
oh, I thought this was a 3D looking
No.
from the side. It's from the top. That's land, right?
Yes, this is the river here.
There we go.
Okay.
Okay, sorry. Okay.
Connecticut.
Okay, here's what we want to do. We got the amount of fence is 3,000 feet. We want to maximize the area enclosed. Okay. How should we construct our enclosure so that we have a maximum area? That's the issue. Now, before we do the problem, let's suppose we didn't have a river to use as one of the borders, and we still wanted to make it a rectangular enclosure. What would we do in that case? We would make that what kind of shape in order to maximize the amount of area enclosed? Well, a circle if we wanted to, not rectangular. Okay.
Oh, yeah.
If we didn't want to use a rectangle at all, if we could have any shape we wanted, it would be a circle. The circle is the most economical shape. In other words, for a given perimeter, it encloses the most area. Here, let me ask you this. Let's suppose we want to enclose the most area for a given shape, but we want to tessellate the plane. See, these squares tessellate the plane. They cover the plane. That's what tessellate means. They cover the plane. What shape should we use to be the most economical That is, for a given perimeter, we enclose the most area and still tessellate the plane. Circles don't tessellate the plane, they've got gaps. What would be the most economical shape to use? Square is not the most
Triangle.
economical. Triangle is not the most economical.
Octagon.
What?
Octagon.
Octagon doesn't tessellate, doesn't fit in.
Probably hexagon.
It is a hexagon. Hexagons tessellate the plane, and they're the most efficient shape to tessellate the plane. And guess what? Bees know this, and that's what they use for their eyes. They use hexagons, the most efficient shape that will cover the plane. Now, if we had no restrictions, circles. If we had to tessellate a plane, hexagons. Okay? If I didn't have the river to use, but I still wanted a rectangle, what rectangle would I use to enclose the most area?
Most
It's not a rectangle.
Wait, what are you asking here?
I'm asking for what shape I would use to enclose the most area for a given perimeter, given that I want to use a rectangle to do it.
And,
My question is evidently not good. Square, you would use a square. You would make a square out of it, and that would enclose the most area for a given perimeter. Okay? It's most circular. Whatever looks more like a circle, that's the way you want to go. Now, here's the question here. The question here is, I've got the river to use as one of my sides to my enclosure. The square is not going to be the best thing to use now. Okay? The best thing to do would be to do what? Make the side parallel to the river longer than the side not parallel to the river and take advantage of the river. Okay? But at some point it becomes counterproductive. Okay? At some point, if you use the whole fence along the river and zero for the other two sides, you get zero area. So that's counterproductive. So there's an optimal point in there where the maximum area is enclosed. That's what we're looking for. Let's do it.
So you're getting 3,000, you need 3,000 square feet, right? Or you,
Yeah, I'm going to use 3,000
what's
feet.
the amount you have?
That's the amount I have to use. I'm going to use all this fence, okay? And I want to enclose the maximum area. You ready?
So, don't you have to make all the little weighty things to enclose it perfectly? The parallel wall of it?
I'm not sure what you're saying.
You said that it has to be the wall has to be parallel to the other.
This wall is
Yeah.
parallel to the river, yeah. The river, I don't need the fence along because the river is going to keep my cows in. They're not going to cross the river, okay? So, I'm going to have some fence here, and some fence here. And what I want to do is maximize the area enclosed. Capital A, the area. I want to maximize this. Okay, I'm going to maximize the area. But what do I know? I have restrictions on X and Y. The restriction that I have on X and Y, called a constraint. Okay, that's a restriction on the variables. Okay, I have a constraint. What do I have for a constraint? What do I know about the relationship of X's and Y's here? Yeah, it's correct. X plus X, 2X plus Y is equal to 3,000. Because that's all the fence I have. Okay? What that enables me to do is to redefine the maximum, A, in terms of a single variable. Okay? And all the problems we do, all the max-min problems that we do, you will have to express the quantity to be maximized or minimized in terms of a single variable. Right now it's in terms of two variables. But given my constraint, where I can solve for y, substitute it in here, I can now express the quantity to be maximized or minimized in terms of a single variable. That's what you're going to have to do for every one of our max-min problems. In addition to that, what you should always do for these max-min problems, Carolina, what? Go ahead, ask away.
Why did you put X in front of the A?
Say that again?
Why did you put the X in front of the fence?
Why did I put this? X, the area is X times what? Length times width.
Oh,
Okay, that's the area of this rectangle, and that's what I want to maximize, that area.
And 2x plus y is the perimeter.
And 2x plus y is the amount of fence that I have.
So that's the perimeter, right?
Well, the perimeter is also this, but it uses the river. The amount of fence I have is this here, 3,000. So x plus y plus x must add up to 3,000. That's all the fence that I have.
And then you took 8 equals x times 3,000 minus
Also,
2x?
y
Yes.
is 3,000 minus
Yes.
3,000. Oh, okay.
Yes, and I substitute that in for y.
Okay.
I need to express the quantity to be maximized or minimized in terms of a single variable. In addition to that, what you should always do is locate endpoints to the problem. In other words, for x here, what are my restrictions on x? X is going to have to be greater than or equal to what? 0, okay? I can't use a negative number for my length of fence.
I'm sorry, I was distracted.
Okay. What I'm telling you is that I have certain restrictions on x. X has to be greater than or equal to 0. I can't have a negative number for x. And it's got to be less than or equal to 3,000, 1,500 would be more of a restriction, because if x is 1,500, I have 1,500, I have 1,500, y would be 0. Okay, that would be a restriction on x. I couldn't be greater than 1,500 because that would make y negative, and that's not allowed. So these are my endpoints. It's important when you do max-min problems to identify endpoints. Yes?
You could have put 3,000?
Well, 3,000 is, but I can do better. 1,500, x can't go beyond 1,500. Because if it does, y would go negative, and I can't have y be a negative. You see what I mean? If x is beyond 1,500, greater than 1,500, 2x would be beyond 3,000, and y would be negative, and that's not allowed. So that's really the end point here. Hey, Danny, you made it.
I passed it because the door's closed.
You just closed it like just 1 second ago.
Yeah, I know. I was like, is that the class? I don't know.
What'd you do? See her coming? You decided to shut the door?
Hey,
That was pretty good timing.
That was amazing timing. That's incredible. Danny, here's what we've done. We've got videos on YouTube now. Okay, we can tell you the address. Okay, and you better get on there pretty soon too, because they're going viral. I mean, they're all over the place now. So you may not be able to get to them.
it's $1.
Oh, yeah, that too. I didn't mention that.
$1?
No.
I was like, I don't have money. That's all. I don't have that.
YouTube's
Okay.
free.
It's
You
free.
exit out all like the stuff we've said.
Yes.
Yeah.
So I have the last class, but in addition to that, we have pictures of all my notes on WebAssign. So if you go to WebAssign, you'll go to the resources, and you'll have the notes for the last couple of classes in there.
It'd be good money, you know, good at making business
No,
out
no,
of
no.
Bird's class.
Did we come up with a date for a test? No.
Oh, we have a schedule. This is on the notes.
Thursday.
Here.
Next Thursday?
Here we go. This is on the notes on WebAssign, but here they are. Here.
No. It's Monday.
That's the rest of the semester right
It's
there.
actually tonight.
You just did it? Oh, yeah, it is Monday.
Okay. All right, what we're doing today are max-min problems. This is the end of the chapter. And we're talking about what are called differentials, which are another application of the derivative. Not so important anymore, but I do want to mention it. There are a couple of homework problems on it. They will not be on the test, however.
Maximum.
Yes, this is the max-min problem. Okay. So here we go. We're going to maximize xy. We're going to maximize the area enclosed, okay, in this rectangular enclosure. Okay. Given that 2x plus y, the amount of fence that we have, is equal to 3,000. This is a constraint. It enables me to get the max-min in terms of a single variable. We've identified endpoints for x. That's important when you do max-min problems, because what could happen is the calculus that we're going to use to solve the problem may not actually give us the answer to the problem. But the answer to the problem will be either a critical value that the calculus will identify or an endpoint, okay? Which is something we talked about at the very beginning of this chapter. Where do you have maxes and mins on a closed interval? Well, it could be a critical value, but it also could be an endpoint, okay? So, if this is going to have a solution, it's either going to be a critical value that we get from doing the calculus, that is, taking the derivative, setting it equal to 0, or one of these endpoints, okay? That's the only two places we can find, where we can find max-min solutions, okay? All right, so here's what we're going to do. Here's our function in terms of x. What I'm going to do is locate the critical values. Let's find critical values. Okay, you find the critical values by setting the derivative equal to 0. Well, I'm going to multiply it out first. Take the derivative. And set it equal to 0. After all, that's where we find critical values. Take the derivatives, set them equal to 0, derivatives equal to 0, or where the derivatives don't exist.
The square come
But-
from?
What's that?
Where did the square come from?
This here?
Yeah, where did the square
X
come
times 2x.
from? So you multiplied x times.
Yeah, I multiplied through. I could have used a product rule, but it looked easier just to
And what was
multiply
the
through.
point of that? To the right? Moving it to find y.
So we could get this in terms of a single variable. That's what you must do. So by doing this, finding y, I can express my area in terms of a single variable.
Okay.
Now I'm multiplying it through and finding the derivative. Damien,
Wait, why are you finding the critical values again? I'm sorry.
I want to solve the max-min problem.
Yeah.
I want to find out which value of x gives us a maximum area. And how do I find that how do I find that maximum value? I find it by locating critical values or locating endpoints. That's the only places I can, that are eligible to be solutions to the problem. So I'm doing the critical values now.
And next
Critical,
then?
oh, sorry, no.
Go ahead.
Critical values and roots, or what are they again?
Critical values are where the first derivative is equal to 0 or where the first derivative does not exist. I don't have that option here because I have a polynomial, and for polynomials, first derivatives always exist everywhere. Okay, there's no place where this derivative does not exist. Carolina,
Did we find endpoints yet? Or no?
yes, we got endpoints here. X is between 0 and 1500. Those are the endpoints.
Now, if it was harder, I understand how you got it, but what if it was like something harder to get, for example, than just by dividing by 2, 3,000 divided by 2? To find the very, how did you find that using mathematics, the 1,500?
Where'd you get 1,500? Oh, this. Okay. Yeah, just by thinking about what can I possibly have
And you're
for a
saying
restriction.
3,000, so X can't be more than
I
half. of it.
understand, but
Yeah, there you
I'm
go.
saying if there's a harder problem.
Oh, then it may be difficult.
Where, how would you
You're
find
gonna
that?
have to use-
Well, it may be more difficult to do.
Yeah.
That is the case.
Because that's usually
Use
the
your
case.
brain.
Yeah, it may be more difficult to do.
You have to be smart.
Matter of fact, I'm going to do one. The last problem that I'm going to give you, one of my favorite problems of all time, as a matter of fact, I'm going to share with you guys.
Your secret.
We're going to have endpoints on that one, and it's an interesting problem. All right, but anyhow, so far the derivative, I'm going to set it equal to 0. Now I'm going to solve for x, okay? Add 4x to both sides, so I get 4x equals 3,000. Okay, add 4x. Divide by 4. Say that again? 750, thank you. If x is 750, what's y equal to? Put a 750 in here. 2 times 750, 1,500. Y would be 1,500. Okay, we're talking feet. This is our candidate for the dimensions that will maximize our area. Okay? Now, we should see if we have a maximum or a minimum. And you determine whether you have a maximum or minimum by using the second derivative. Okay? If the second derivative at this point is positive, that curve is concave up. Second derivative positive means it's concave up, and we have a minimum value. If the second derivative is negative, it's concave down, and we have a maximum. Let's take the second derivative and see what we have. It's -4. That means this is concave down. That means we have a relative maximum. Now, the question is this the absolute maximum? We know it's a relative maximum. Is it the absolute maximum? Is it the solution to our question? And here's what you have to do. The solution to our question is going to come from two places. Critical values, which we have this one, or endpoints. Let's test the endpoints to see if we have a maximum value at an endpoint. Well, one endpoint is x equals 0. What's the area enclosed if I use 0 for x? 0. That's clearly not a maximum. What's the other endpoint when I use x is 1500? What's the area enclosed when x is 1500?
0.
0 again. I have zeros at both those endpoints. Clearly not the solution to the problem. If the problem had been find the minimum enclosure, the minimum area, it would be either endpoint where you get 0. But since we want a maximum enclosure, maximum area enclosed, it occurs at this point when x is 750, y is 1500. The maximum area is the product of these two. 750 times 1500.
1,125,000.
What is it again?
750 times 1,500?
Yeah.
1,125,000.
Wow, that's surprising. Oh, I had a lot of wood though. Okay. 1,125,000 square feet of area enclosed. Well, I could put a lot of cows in there. Lots of cows.
Lots of beef.
Lots of beef in there. Okay. This is a typical max-min problem and how it's solved. Danny.
But if you plug in 0 to the y equals 3,000 minus 2x,
Yep.
it would not be 0.
If you would let x equal 0, the y would be 3,000. That is
Yeah.
correct. But the area would be 0, and that's what we're testing.
Okay, yeah.
Okay? No problem. Typical max-min problem. This is the kind of thing you're going to see on the test. You're going to see 2 max-min problems on the test. 2 of them. Okay? You're going to have 2 graphing problems on the test. 1, okay, cubic polynomial, third-degree polynomial. I'll tell you right now. 2, a rational expression, okay, with vertical asymptotes. You're going to have 2 graphing problems. You're going to have 2 max-min problems to do on the test.
Would you say 1 cubic?
And 1 rational expression, x over x plus 1, something like that.
Is it just graphing them? Or-
Well, I'm going to ask where it's increasing, decreasing, concave up, concave down, horizontal tangents, that kind of a thing. I'm going to ask you those questions. Damien. And wait, one other thing. And also on the test, you're going to have a mean value theorem problem to do. You have to find the c in the interval where f prime of c is equal to f of b minus f of a over b minus a. I'm going to give you one of those, at least 2. At least one of those. Damien.
What's the second derivative? Tell us again.
Whether it's concave up or down.
And in this case,
Points of inflection.
it's negative, so it's pointing down, so it's going up.
So it's down, it's concave down, so we got a maximum value.
How does that,
Because it's like this, concave down.
There you go.
I understand that whole concept, but like, how does that pertain to the area of the town?
Because at that point in question, that critical value, the curve, that is the area curve, is down like this. That's what the second derivative is telling us. So, and we found that point up there. So we found a relative maximum value. If that first derivative had been positive and the curve is concave up, we would have found a relative minimum value and clearly not the solution to our problem. But since we got a relative max, it's a candidate for a solution.
Oh, okay.
Yes?
That's 25.826 acres.
Good deal. All right, 43,250 or so square feet in an acre. 40,000 goes in there, whatever time. What'd you say, 20-something
I
acres?
just looked up.
Oh, good. All right, go ahead.
What's the mean value thing?
Mean value theorem is you get a function, f of x. You find its derivative. And you find its derivative at c. And somewhere in an interval that's given, you're going to find a c where f prime of c, the slope of the tangent line, is equal to the slope of the chord or the secant line that connects 2 points on the graph.
Do you know if I was there that day?
It could be that you weren't. I proved it. Do you remember the proof?
I don't remember. I might have.
Okay, well, check it out. If you don't have it, I will prove it for you sometime. After class, or
Yes.
before class next time if you get here early.
Yeah, I can get here early.
Well, if you get here early,
I just decide not to.
Oh.
okay,
No, the parking's bad.
Okay.
I need to search.
okay. Okay. Any other questions? Yes, Carolina.
So if the question would ask about minimum, right?
If it were, yes.
Yeah. Would we still have to multiply the x and y together to find?
The area, yeah. If you want to minimize the area, that's still the quantity to be minimized in that case. You would do everything the same, except at the end, when you found the second derivative to be negative, you know your answer is not a minimum, it's a relative maximum. So that's not the solution. Then you would look at the endpoints, and you would discover that the endpoints give you 0 areas.
Should we let him in?
But if it was positive, then you would look at critical?
If when doing this problem, looking for a maximum, we found the second derivative to be positive, and we had a minimum, and we wanted a max, you would look at endpoints, yes.
So we're gonna do another example.
I'm going to do a couple more examples.
Do
Okay.
it.
I get it.
Okay, ready? Let's do another example. We're going to do a few examples.
I did have it in my
This
notes.
is kind of like those, whatchamacallits.
Yeah, those.
Yeah.
The one with Shambo and his buddy leaving SeaWorld.
Oh, yeah, that's true. That's a related rate problem.
Yeah.
A little bit different. Related rates always take the derivative with respect to t. These max-min problems, you always take the derivative with respect to the independent variable. Remember I said to get the quantity to be maximized or minimized in terms of a single variable, you take the derivative with respect to that single variable, always. Okay? Set it equal to 0, solve it, check it with a second derivative test, and then look at the endpoints.
So related rates always
Always with respect to t, always.
time.
Yep, always with respect to time. All right, let's do another problem. You ready?
Let's go.
Here's the problem. Here's what we want to do. We want to find two real numbers, x and y, both greater than or equal to 0, such that two things. First problem, 1, the product of x with y cubed is a maximum.
Is it a P?
P, product, yep, is a maximum. 2, the product of x with y cubed is a minimum. So there's two problems. So we got, and there's a constraint, x plus y is equal to 100. Okay? So we want to find two numbers that add up to 100 such that the product of the first with the cube of the second is a maximum. It's one problem. Second problem is find the two numbers whose sum is 100 such that the product of the first with the cube of the second is a minimum. Any ideas for the maximum?
Minus x plus 100.
Excuse me?
Minus x plus 100 equal to y.
All right, solve, well, yeah, but before we do the problem, that's exactly right. But anything's off the top of your head, any intuitive feelings as to what the solution should be for the maximum? You're going to find two numbers who add up to 100, but the product of the first with the cube of the second is a maximum.
So that x has to be this very, very small for the maximum?
Smaller than the y, for sure.
Yeah, a lot smaller, and then y cubed.
Okay, yes.
How can you have like the same thing be a max?